Hello, everyone, and welcome to Chapter 5 Notes. We are going to be going over the high points of the notes for Chapter 5 for Chem 1115, Chemistry and Society. And again, as I've mentioned in previous videos, this is just a summary of what's in the notes. I still encourage you to go and make sure you read all of the chapter and contact me if you have any questions. So in Chapter 5, we're talking about water, the most precious resource, and some guiding questions to think about. What are the properties of water? Water is actually a really unique molecule, as we'll talk about. Where is water located and how is it used? How does water interact with other things? And what can we do to improve water quality? So this is your reflection. You'll be doing this on your own. Let's talk about water. Water is ubiquitous. That's a fun word. Ubiquitous just means everywhere. So if you want to impress someone with your vocabulary, use the word ubiquitous somewhere today. So this is funny. My kids actually have this same problem. They say, water, it composes 60% of our body. And they think that they've got this like giant lake somewhere in your body, right? And when it says that, that doesn't mean that literally you've got this, big giant puddle somewhere in your body that accounts for 60%. The 60% means that it's in every single cell. It's in your blood. It's, it's everywhere in your body. And so, as you know, it's essential for life, and we can only survive a short period of time without it. And so one of the things that you could do to kind of get yourself aware of the amount of water that you're utilizing is make a water log. So pick some time, pick 2 days, and record all your activities involving water, and then think about how much you're using. So fresh water is a rare and precious resource, and only 3% of the water on our earth is fresh. And so that's a small amount. Right? If you look at this pie chart here, saline, that means salty, in the oceans, it's 97%. And the freshwater accounts for only 3%. And if you take that out of the freshwater, how much of that is in ice and glaciers, and how much of that is in water, and how much of that is in surface water? It's 0.3%. And most of that is in lakes, and the remainder is in swamps and rivers. So just something to kind of put it all into perspective. Lots and lots and lots of water gets used here in the United States every day. I watched a recent documentary, and these videos have been around for forever, about how the geography of our country, where cities are located and how cities are defined, and even states, how they got their shapes, all are tied to water. Because without water, you can't live. So something interesting, if you like studying history, you can go see how water and just access to water has shaped this country just geographically, as well as where people live. So this is something for you to read over on your own. It's a water footprint and estimate the amount of water used to make a particular service or particular good. Something to think about. Before you throw something away, you could always think to yourself, wow, I probably shouldn't throw away this rice. I should eat it, because look at how much water it took to make that rice. And here's what I was talking about at the beginning of this lecture. Water really is an unusual molecule, and you need to make note of these details because you will be seeing them again. Water's a liquid at room temperature. It's a liquid under standard conditions. And that's not something we think about every day because, I'm sitting here making this lecture and I've got a glass of water on the table. And you grow up with water around you. You don't even think about it. But the reality is all the other compounds that have similar masses are actually gases under these conditions. So oxygen gas, nitrogen gas, carbon dioxide, those all have similar molar masses. And so the fact that water is a liquid with a similar size to these other molecules is really unique. Water also has a really, really high boiling point. 100 degrees Celsius is pretty hot. And liquids of similar size molecules, like hydrogen sulfide, have a much, much, much lower boiling point. Again, because they are gases at room temperature. And then the other thing that's really, really unique about water is that it expands when it's freezing. And again, this is not something that we stop and think about on a regular basis because everybody's used to being able to go in your freezer and grab whatever amount of ice you want, right? But if you take your cup and you throw some ice in it and it floats, you never stop and think about that. But the reality is most substances, when they go from the liquid phase to the solid phase, they actually solidify and they get contract, they sink. So if you think about any other liquid, if you freeze it, the solid would sink to the bottom. But with water, it actually expands, and that's unusual. So why ice floats is one of the unique properties of water. And the reason that ice floats is because it's less dense. I mean, that's the reason anything floats on anything. The less dense thing is on top of the more dense thing. And so liquid water is more dense than ice. So when you make ice, the water molecules actually spread out. So you're taking the same mass and you're spreading it over a larger volume. And that means that the density goes down. And so you might be thinking, well, who cares? If you are an animal who lives in a pond and it's winter time, you care a lot, right? Because frogs and fish and all those creatures, they survive the winter because ice floats instead of sinks. If ice sunk, then ice would sink, and then a new layer would sink, and then a new layer would sink, and then a new layer would sink, and eventually the whole pond would be frozen, and all of those creatures in the pond would all be dead. So aquatic animals are very, very interested in the fact that ice floats. And the next time you're drinking a drink and you see your ice floating around in there, you can think about that and explain it to your friend, and they'll be super impressed. All right, a solution is another word for a homogeneous mixture. We learned that word a few chapters ago. A homogeneous mixture just means a mixture where the composition is uniform throughout. And so a solution forms when a solvent and a solute combine. So a solute is the substance that's being dissolved, and the solvent is what you're dissolving in. And anytime water is the solvent, that's called an aqueous solution. So for instance, if I get my cup of water and I take a scoop of sugar and I put the sugar in the water and stir until it's dissolved, the solvent would be the water and the solute would be the sugar. And I would call that an aqueous solution. All right, this table right here is something that will be on the reference page for your exams. You've probably already noticed it there and wondered what it was. This is called the solubility chart. So not all substances dissolve in water. Some substances are called insoluble and other substances are called soluble. Okay, so if something dissolves in water, we say that it is soluble. And if something is unable to dissolve in water, we call it insoluble. And so this chart is called a solubility chart. And if you want to know if something will dissolve in water or not, you look at this chart to help you. And so water pollution is something that's really important to us. I'll let you read over that on your own. This slide's actually in the wrong place. Water pollution comes from a lot of different sources. And again, you can read that on your own. Here's what I was trying to get to. I put those two slides about pollution in the middle of my solubility chart. That's okay. So let's practice this so that everybody understands. Okay, so the way you do this, and I don't know why it's not, there we go, is you look at your salt and then you look what's in that salt, and then you look at your solubility table to figure out, is it soluble or not? So for instance, this first one is called lead 2 nitrate. So we look up either PB in the chart or NO3 in the chart. Well, there's no PB over here, but there is NO3, that's nitrate. So nitrate, all of them are soluble and there are no exceptions. So the answer to this question would be soluble. Yes, that is soluble. All right, CaSO4. Well, there's no Ca listed as one of my ions, but there is SO4, sulfate. So most of them are soluble. However, these ones are not. Strontium sulfate, barium sulfate, lead sulfate, silver sulfate. Okay, so calcium's not listed as one of these exceptions. So that means that calcium sulfate would be soluble. All right, Na3PO4. Again, I don't have any Na on here. And actually phosphates aren't on here either. That's a problem. So let's just, for the sake of argument, let's change it. Oops. SO4. Okay, because I don't have any phosphates on here. So SO4, we look at it again. There's SO4. Most of them are soluble. There are only 4 exceptions. Na is not listed as one of those exceptions. So I would conclude that this one is also soluble. Okay, now let's do the next one. AlOH3, fine hydroxide, is right here. Insoluble, with the exception of NH4. Well, I've not got NH4 here, I've got aluminum. So that means this one is insoluble. And then Br, let's see, I don't have any Brs on here, so let's do chlorine. Change it up. Okay, Cl. Most of them are soluble except silver, mercury, and lead, where they're silver. So I would conclude that this is insoluble. All right, so that's how you use the solubility chart. You just look at the ions and then you look to see what the answer is and if there are any exceptions. And you need to be able to do this because that is something that's going to be on the chapter quiz and it will be on the exam too as well. And I will give you this solubility chart. I'll give you this one that's right here on the exam. It's on the reference page. Okay, electrolyte. You've probably heard this word when you're looking at a sports drink. It'll say contains electrolytes. And some people are really impressed by that because they think it's some fancy chemical. But an electrolyte is just a solution that can conduct electricity. That's all it means. So if you put your probes into the solution and the light bulb turns on, then it's called an electrolyte. And if you put your probes into the solutions and the light bulb does not come on, it's called a non-electrolyte. So for instance, if you dissolve sugar, that is a non-electrolyte. If you dissolve salt, that is an electrolyte. And if you've taken biology lately, I know a lot of biology classes talk about this principle, like dissolves like. And here's what that means. The shape of your molecule determines whether or not it'll dissolve. And if you go on to take future chemistry classes, you will spend a lot of time talking about this concept in great detail. But for here in this survey class, that's as far as we're going to take that. So the shape of the molecule determines whether or not it dissolves. If the shape of the solute matches that of the solvent, then it will be soluble. And if the shape of the solute molecule does not match the solvent, then we'll say it's insoluble. So this would be an example of insoluble, right? This is water, this is oil. You know the phrase oil and water don't mix. Well, why is that? Water is a small molecule. Oil is a big, long, hydrophobic molecule. And so that's a big way of saying the shape of the oil is not compatible with the shape of the water, and that's why you get those layers. All right, pH is something you've probably seen in your past as well. It's a measure of acidity or basicity, depending on which way you're looking at it. And the pH scale ranges from 0 to 14. Now, we're not going to be doing any pH calculations in chemistry and society, but if you go on to take other chemistry classes, you will definitely be doing pH calculations there. Here, all I'm asking you to do is interpret a pH and then decide if it's acid, base, or neutral. So if the pH is less than 7, it's called acid or acidic. The pH is greater than 7, it's a base or basic. And then if the pH is 7, then we say it's neither an acid nor a base, it's called neutral. And acids and bases have different chemical properties, which you'll learn in great detail if you go on to take other chem classes. But right now, you just need to know that they have differing properties because they're different substances. And when an acid and a base react, we call that neutralization. So here's the pH scale. You've probably seen something similar to this before. 0, 7, 14, right? So your acids are all down here, stomach acid, lemon juice, soda, tomato juice, acid rain can be in this range. Milk's getting closer to neutral. There's pure water. Blood is ever so slightly basic. Then we've got seawater. This is a medicine you take milk of magnesia, helps you with constipation. Ammonia, oven cleaner, right? This is lies, nasty stuff. Very, very basic. So why is rainwater, just naturally occurring rainwater, slightly acidic? Well, it's because there's carbon dioxide in our atmosphere, and that carbon dioxide dissolves in water to form carbonic acid. So naturally occurring rain is ever so slightly acidic just because of the fact that carbon dioxide is in the atmosphere. The acid rain is when the pH drops lower than what you would normally expect. And it's not from carbon dioxide, it's from pollution. So sulfur oxides and nitrogen oxides dissolve in water droplets in the atmosphere, and then that makes the pH of that rainwater drop, and then you've got water that is acidic, and now it's really dangerous for your environment. It can do a lot of bad stuff, as this picture portrays. So the pH of the ocean, you would say, well, if rainwater is a little bit acidic, why would ocean water be a little bit basic? And so there are three substances that are kind of bouncing around in equilibrium that maintain the pH of the ocean. And you don't need to know this for a test, but just for your knowledge, there's carbonate, bicarbonate, and carbonic acid. And ocean pH decreases because of pollution, more or less. So just something for you to read about on your own. Over time, the pH of the ocean has been dropping, and you see that in things like, you see the effects in that in coral reefs and things like that. And so what happens to ocean life, or freshwater for that matter, when the pH changes? So we living things have a very narrow range of tolerance that we have for changes in our pH. We like our environment to be homeostasis. We want to maintain a constant internal environment inside our bodies. So that means that we don't have a huge range of tolerance for changes in our environment. And plants and animals in oceans are no different. So if pH goes below 4, and that lake's toast, there's nothing there. And normal range, this is coming from decomposition of fish poop and other decaying matter, right? That's going to naturally make the pH go up because you have amino acids and things that are dissolving in those proteins and all that good stuff. But over time, it can go down from pollution. And so this is something for you to just skim over for your knowledge about how water is treated. And one of the things that could be a potential option for the future for getting fresh water is taking salt water and making it into fresh water. The problem is this is really complicated. It takes a lot of work. And so you can do this in the lab. I actually have my students do this in other chemistry classes. It's called distillation. And so you're separating a liquid from a mixture. And you can actually do this yourself if you go on to future chemistry classes. You'll take your water or your mixture of liquids and you put it over heat. The liquid water boils and then it condenses here in this condenser. And then you've got your pure water over here and all the salt is left behind. And here are some of the ways that we can also do it on a larger scale than what you would do in the lab. Osmosis and reverse osmosis, which you've probably read on water bottles and things like that when those companies talk about how the water is filtered or treated. So that's where we're going to stop for chapter 5. And as always, if you have any questions, please feel free to reach out to me. And I hope you are having a good day, and I will talk to you next time. Bye.